Yeah, you can start.
Okay. Welcome everybody to lecture 10. So we'll continue our module on expanders. In particular, we'll talk about random walks. And last time we talked about random walks and general graphs, and then we talked that in general graphs, the argument showed any connected non-bipartite graph, if you walk randomly starting from any starting distribution, you will converge to the stationary distribution on the graph in polynomial number of steps. Polynomial number of steps. Polynomial number of steps. But somehow expanders were mixing much faster. In a logarithmic number of steps, you would actually converge to the stationary distribution. In the case of deregular graphs, the stationary distribution is uniform distribution. In that sense, sort of. So Neha had asked this question: what happens if if lambda is 0? Lambda is 0 for the case when the graph is a complete graph. That is, every vertex has an edge to every other vertex, including itself. This is the complete graph with self loops. This graph mixes in just one step. You just take one step in this graph and it mixes. And the expander graph comes as close to it as possible. It also mixes very fast, not necessarily in one step, but logarithmically many steps. But on the other hand, it is extremely efficient in compared to the complete graph. The complete graph has something like order n square edges, whereas the expander has only dn edges, and d can be made a very small constant. It can even be made a constant as small as 3. Therefore, it's a much smaller number of edges, and yet it behaves like the complete graph. What we'll show today is we will expand on another aspect of random graphs. We have another aspect of random graphs, and we'll show on random walks on expanders. So we will show that yet another property of a random walk on expanders looks like the complete graph. So in a complete graph, so what's a complete graph again? It's n vertices, and you have an edge from every vertex to every other vertex, including itself. Let's look at a t-step walk in this graph. What is a t-step walk in this graph? A t-step walk is just picking independently t vertices in the graph, because every vertex is connected to everything. So a t-step walk just picks t vertices independently in the complete graph. Now let's look at what happens, the same phenomenon in the expander graph. That is, start at a random vertex. Now, unlike the previous case, you're going to start from a random vertex and then take a t-step walk in this graph. And then we'll ask, how do these t vertices look like? Notice these are very correlated vertices. That is, given the first vertex, there are only d choices for the second vertex, and then d choices for the third vertex, and so on. It's very limited choice. Yet we'll show somehow this sequence of t vertices behaves as if it's coming completely independently. That's the main property we are going to show today. In particular, we will show what is the following aspect of random walk on expanders. We do the following lemma, which I will call the hitting set lemma. I'll state in a second why I call the hitting set lemma for random walks. On expanders. So let G be a expander on n vertices with spectral gap 1 minus lambda, with lambda being strictly less than 1, and in particular, just recalling what lambda is. Lambda is the max of lambda 2 and the absolute value of lambda n. And let M be the corresponding random walk matrix. Now let B be any subset of the vertices. So this is a vertex set. So B is any subset of the vertices. and let pi of b be mu. That's the density of the set B under the stationary distribution. In case this case, the stationary distribution is a uniform distribution. Actually, I don't need this. Yeah, one. And let x1, xt be a random walk of length t, starting from the initial vertex x1, which is itself sampled from the stationary distribution. You pick a completely independent, you don't pick a worst case, you pick a completely independent starting vertex and then take a t-step walk in this. What we're going to ask is the following question. Then probability over this choice of x1, x2, xt. So notice what is the randomness involved over here. The randomness involved over here is the choice of the first vertex and then the choice of the second vertex, which is one of d choices, the choice of the third vertex, which is one of d choices, and so on. For this, we'll ask what is the probability that this entire sequence never leaves the set B. That's the probability we're going to count. Okay, that's what we want to ask. Now, suppose this were a complete graph. It was not an expander. Suppose it were a complete graph in which x1, x2, xt are just independent vertices. They are not neighbors of each other. You pick the first vertex x1 at random, then you pick the second vertex x2 at random, all from the stationary distribution, from the distribution pi, and so on t steps. What is this probability?
Pi, like mu to the t.
Sorry, I didn't catch you.
Mu to the power t.
Mu to the power t, because the probability, it's independent, so it just splits into a product. The and becomes the product of and. The probability of disjunction of events becomes the product of the probabilities, and each thing is mu. So this is mu to the t. If lambda were 0. But now what we'll show is it's almost this. It's mu times mu plus lambda 1 minus mu whole to the power t minus. So if lambda is 0, I recover the same previous result. But the main difference is it's mu times, it's this, instead of going mu to the power t minus 1, it's mu plus a small extra constant. As the smaller lambda is, this additive term is very, very small. So it behaves more or less like the complete graph, a random walk on a complete graph where t steps are picked independently. Here t steps are picked in a very correlated fashion, yet the probability that the walk remains fully in step B is very, very small. It behaves exactly like more or less like the complete graph. So let's chew on this statement a little more. So this will be the large part of today's lecture. We'll be trying to understand the statement and proving the statement.
Condition on the path seen so far, the next step is taken according to pi, or like pi restricted to that vertex, or how?
The next step is it's just picked as a random neighbor.
Okay.
It's picked as a random neighbor. Notice that the marginal on every vertex is in fact mu, because you start with the first vertex mu. The marginal is pi. The first vertex is picked according to the uniform distribution, the stationary distribution. Now you take a step. Because it's a stationary distribution, the next step is also according to the stationary distribution. So each xi is distributed exactly according to pi. But the point is they might be correlated. There's no reason why. That is, each of the xi's could be the same. For instance, I could have picked each of the xi's could be the same vertex. In this case, this probability is not mu to the power t minus. It's not this small. It is just mu. It's a probability that the first vertex falls into B. So the marginal on every vertex in each of the xi's is in fact the stationary distribution pi. But the point is the joint distribution. The joint distribution, does it look like as the product of pi? It certainly does not look like that. It doesn't like the t-wise product of pi, because Once you know the first guy, there is only D choices for the second guy, and so on. But yet, this event, all I'm saying is this event, for respect to this event, these things look as if they are independent. So, Sean, to answer your question, and
yeah.
So each step is picked according to the random walk matrix. You are at a particular step, you pick the first step is picked according to the uniform distribution of the state, which is according to stationary distribution, which is the uniform distribution of the graph is deregular. Then the next step is picked by just as dictated by the random walk matrix. So you go across this. So if you pick a vertex uniformly at random from the D neighbors of the vertex and keep walking. And so you look at this T-step walk. Notice the so let's make some. I want to make some remarks on this. The first remark is, of course, if or rather G were the complete graph with self loops, in which case I'll call this M independent. That is, the random walk is independent. Each step is not looking at the previous step, it's comparing this one. Then lambda is 0, and you recover and you get back this. Let's call this star. In this case, star is less than or equal to mu power t, which is the right answer, which we believe. So it's a sort of a strict generalization of the thing which we have for complete graphs. Now I want to show that this actually has an application to de-randomization and stuff. So before we go into the proof of it, let's try to understand the statement of the theorem a little more. So we'll see an application of this and then go into the proof. So once again, any questions on the statement of the lemma? Not. So let's see an application of it. Let's see the power of it, and then let's go to the proof. So let's spend the next 10 minutes on the application, and then we'll go into the proof of this one. So recall, we had previously done this a few lectures ago. We had done this theorem due to Karp, Pippinger, and Sitzer. It said the following, that is, if G is an n vertex deregular n by 2/a vertex expander for some a strictly larger than 1, then B is some set of vertices such that mod B is less than or equal to B over 2. So you pick some set of vertices again, B, and ask what is the probability that if pick a random vertex from pi and look at a t radius around. Look at that BVT, the entire ball. So what's the entire probability? The ball is contained in B. We had shown that this is less than mu times a power t. A power t, yes. This is what we have called Karp, Pippinger, Sitzer, and proved this. And this was useful for de-randomization. In what sense? Let's just recall that application too, and then I'll see how the lemma which we proved today is actually a slightly gives in some sense a better result. So what we had shown this an KPS was towards RP error reduction. So you could reduce the error from half to delta. And basically what did we do? We basically that was basically by setting mu to be equal to half and the and you want it, therefore, mu by a power t to be less than or equal to delta. You just get it by setting some delta to be t to be order log 1 over delta by log a. This will give you the result. But this was this one, but what's the number of repetitions you need to do? The number of repetitions you need to do for this is you have to do it for the entire ball, the size of the ball BVT, which is roughly d plus 1 to the power t, which is d plus 1 to the t. This is polynomial in n. Polynomial in what? Polynomial in n, small n, provided t is order log n. So conclusion of this, putting all of this was a conclusion of this. Conclusion of this was, just 1 second. Sorry, that was an important call. Okay, so the conclusion of this was the fact that you could reduce error from half to any inverse polynomial without, so that you could make delta to be any inverse, you could choose any delta, but the point was, if you want to choose delta, you need to choose t to be log 1 over delta. Log 1 over delta. So now what are all deltas that are possible? The question is that t is restricted by the fact that t can be at most order log n. If t is more than log n, the number of repetitions becomes super polynomial. You could not have done this process. Therefore, you could reduce it. You could reduce half the error from half to any polynomial without paying an extra random point, without paying any additional randomness. Of course, this immediately begs the question, if you can get it to inverse polynomial with any addition, can we reduce the error further? Can we reduce error further, say to inverse exponential? Either without adding any random bits or possibly paying a few extra random bits. That was once you had the Karp-Pippinger application, this was what was left behind. So the natural question to ask, if once we follow the Karp-Pippinger application to de-randomization, and what the hitting set lemma says, what we'll see what's happening. Hitting set lemma says is in fact yes by hitting set lemma, and we'll see why is that, and then prove the hitting set lemma. So is the context clear? Any questions on this so far? So what's the difference between the hitting set lemma application and this one? In the Karp-Pippinger Sipser, sort of the clouds which we were picking up were balls of radius t, and in the hitting set lemma, what the sort of the t vertices we are picking up are not balls of radius t, but walks of length t. And what we are asking over here is the entire ball contained in the bad set B? And here we are asking, is the entire walk contained in the bad set B? So it's a very similar flavor. In one case, you're asking, is the ball contained in the bad set? The second case, you're asking, is the walk contained in the bad set? Now notice what was the, so what's the probability of error? So once again, I'm planning to reduce, it's an RP error reduction. We want to reduce error from delta to half. So you can think of B as the density of B as some half size set, and we want to reduce the error. So what's the error given by, what's the probability that the entire walk is in the set B? This we saw it was mu times mu, what's happening? Mu plus lambda 1 minus mu to the power t minus 1. This is sort of like mu, and lambda is half. So this is 1 plus mu by 2, the whole power t minus 1. Sorry, what am I saying? This is half. Mu is half. So this is 1 plus lambda by 2, the whole power t minus 1. I'm going to say that this is, the error is so much that I'm going to just replace this by 1 plus lambda by 2, the whole power t. Notice this number is not like 1 by 2 power t if you've done independent repetitions, but it's like 1 plus lambda by 2, the whole power t. It is still a number. So it's not like half to the power t, but it's possibly like 3/4 to the power t or 9/10 to the power. It is still a number less than, it's still a number. So this is still some c to the t for some c which is strictly smaller than 1. So it still goes down exponentially in t. Therefore, you can make what am I stating? If you take t steps in the walk, you can make the error go down exponentially in t. Therefore, if you take a t step walk, the error goes from half to exponentially in minus t. And let's look at the other parameters. What is the number of random points you used? The number of random points you used is the first step is log n plus t minus 1 times log d. This is the total number of random points that we need. The first thing you have to pick n, a random vertex, and then you have to pick t minus 1. For each t minus step, you have to pick a random neighbor. Each neighbor involves picking a random number between 1 to d. And if for d being constant, this is, and n being 2 power n, this is like n plus order t. And what's the number of iterations? The number of iterations is, it's t iterations. So that's what you have to take away from this one. Let's just contrast this to what happened when you work with, instead of this is a t-step random walk versus t independent random point tosses. There, once again, half goes to exponential minus t. This is not log, this will be t times log m. And this will be the same t. So the big advantage between the a random walk on expanders and independent is this suffers a multiplicative loss of t, whereas this is only an additive loss of t. And so you can now set t to be any number you want to. So in particular, if you wanted to, you're allowed up to polynomial number of repetitions. So do polynomial repetitions. You can get the error to be even inverse exponential. I should possibly erase this. This looks to this one along with this. You follow what I mean. Okay. So this performs as good as the random walk, as good as independent random points. In fact, it's, in every aspect, it's better than it. It's, as the number of repetitions is the same thing. Random points, instead of being multiplicative by t, it's only an additive t factor. Additive, it's a linear additive factor. So in a sense, it's superior to the random walk, to the independent things always. So whenever you want to do repetition, you should not be doing the point tosses independently. You should just pick them up from a random walk on an expander graph and do it. But once again, notice what we need for this example is for this application is we need not just an expander construction, we need a super explicit expander construction. We cannot afford to draw the entire graph. That's too many vertices. So given a vertex, we must be able to go what its neighbor is. And in next lecture, we'll actually see extremely efficient constructions of expander graphs which achieve this property. Both these applications should really impress on you why we need the super explicit construction of expander graphs. That is, we need an expander construction which is not just polynomial in the size of the graph, it's actually polylogarithmic. That is, you can talk about the neighborhood relationships in polylogarithmic time instead of polynomial. Any other questions? We'll get on to the proof shortly. In 5 minutes, we'll get to the proof. But let me ask any other questions.
Prahladh, so in the KPS construction, can we compare this to the KPS?
Yeah, the KPS. So what happens in the KPS construction? So if you compare it to the KPS construction, so let's write, so you want me to do it? So let's actually write the error in terms of delta. So let's rewrite this in terms of everything in terms of delta so that I can make a fair comparison between the two. Rewriting in terms of delta. So I'm reducing error from half to delta now. I'm going to be setting delta to be exponential in minus t. What's the number of random coins over being used here? It is n plus order log 1 over delta. What's the number of iterations or repetitions? It is t, which is order log 1 over delta. So this is the, so let's write down, this is the AKS construction. How was the KPS construction? The KPS construction was also a half to delta. The number of random coins was just n. So in that sense, it's better than this one. You didn't use any extra random coins, but the number of iterations was poly in 1 over delta. So in terms of random coins, it's better, but in the number of repetitions you have to do, it's much, much worse than the AKS construction. And let's even put the complete independent thing, that will be number of random coins is order log 1 over delta into n, and number of iterations is order log 1 over delta. So this should compare and contrast the three things. That is, as long so KPS and AKS both are good in certain directions. As long as you don't care, if you want error delta to be only inverse polynomial, KPS sort of dominates AKS because there's no extra random coin that you're using, but the number of iterations is so large. If you want that error to become even smaller, KPS is not useful. If you want the error to become like inverse exponential, slightly smaller than inverse polynomial, then this is no longer useful. Whereas this is now, you can use the AKS, and in all aspects, AKS is better than the independent set. So this chart should sort of tell you how to compare all these three against each other. So very important parameters of these. Okay. Questions? Shubhada, does that answer your question?
Yeah.
Okay. So, actually, even before we go to the proof of the hitting set lemma, all of this was for RP error reduction. Now you can ask, what about BPP error reduction? This is all one-sided. You're asking if the walk is completely in the ball in this bad set or not. But for BPP, we need something stronger. So you can ask question. So I'm going to ask, what about BPP error reduction? Now, if you recall, what did we do for BPP error reduction for general in the independent sets, which was what was the theorem that we used? So you had an algorithm which made error on both sides. That is, in the S side, it gave the right answer with probability 2/3. In the no sem, it gave the right answer once again with probability 2/3. Now you wanted to amplify this. So what did you do? Once again, we took repetition, majority, and then what's the theorem we appealed to? Okay, so it's majority plus Chernoff. That's what Varun says in the Varun. Yeah, somebody said in the chat. Yeah, majority plus Chernoff. Now you can ask, is there a similar Chernoff bound that you see on a random walk on expanders? What is Chernoff bound? So in fact, it is true. So what we will show is that there's a following bound. There's a Chernoff bound for a random walk on expander graphs. And the setup is similar. So let me copy the setup. The setup is going to be similar. So we're going to once again we have an expander graph on V vertices. There's a bad set B, and we pick a t-step walk as before. We pick a t-step walk, but what we will now ask is not, instead of asking is that walk completely in the bad set, we'll ask the following probability, and the probability is once again over the choice of vertices x1 to xt. We'll ask what is the number of times the walk is in the bad set. So we'll ask what is the number of I in T such that xi is in the bad set. Let's look at the average number. What do you expect this to be? What do you expect this to be? So if you pick a vertex, what's the probability that it will be in the bad set? Mu. So I expect this to be around mu. The point is the deviation of this by more than is what we will show. This is like a Chernoff bound. We'll show that this is 2 exponential in minus. Let me write this below. So this is almost like the Chernoff bound. In the Chernoff bound, lambda was 0. You would get this. Here it says lambda is not 0, but as long as it's not something, as long as it's not 1, you get something. It's equivalent to Chernoff bound. It's just that the constant changes. So we have a similar theorem, just like RP error amplification. We also have a BPP error amplification. So notice what is this now? What is this number? Let's look at this number. You're looking at, I'm once again taking a walk. So here the picture is a slightly different picture. It's not, I'm taking a walk of t steps, asking what fraction of the walk is contained in the bad set P. Now, marginally, every vertex is according to the uniform distribution. So each vertex is in the bad set B with probability mu. But these are not, unlike the Chernoff bound, these are not independent vertices. So the t steps are not independent. Therefore, you can't apply Chernoff bound and say what the probability that the fraction of vertices you see in the bad set is fraction of vertices in the walk you see in the bad set is also mu, or close to mu. It's not. But you can use the theory of expanders to actually show that this is almost like a Chernoff bound. You do get such a theorem, which is almost like the Chernoff bound. Notice the only difference from the Chernoff bound is the Chernoff bound did not have this term. And this is equivalent to the Chernoff bound. If lambda is 0, this is the Chernoff, exactly the Chernoff bound which we wrote. And this sort of recovers the Chernoff. And any lambda which is not 1, you get some result. It just changes the constant. So almost the same, this one. If lambda is 1, of course, you get nothing. But for every other lambda, you get something. Okay. So this is this one. We will not prove this in class, but the next problem set 2, will have a weaker version of the Chernoff bound you will be proving. And it will be a direct, it will be using the hitting set lemma. So the hitting set lemma, which we have been stating so far, we will prove it using the hitting set lemma. Okay, that's what will happen. The problem set, we'll prove, you won't prove such a strong Chernow bound, we'll prove something which is just as good for most applications, but you'll use the hitting set lemma that we've been talking about so much but haven't yet proved so far. So let's, without further ado, get to the proof of the hitting set. So let's now start. Spent a lot of time talking about what the hitting set lemma is, why is it useful. Let's go into the proof of the hitting set lemma. So once again, let's go and stare at the theorem statement for a while. Recall what we are trying to prove. We have this, we are starting from a random vertex in the graph. We are taking t steps according to the random walk, according to the expander, and asking what is the probability all these t steps are in a particular bad set. Want to show it more or less looks as if the walk is taken when the t steps are picked independently, not as if they are neighbors of each other. This is what we want to prove. So we want to bound this star probability. Okay, so let's get to proving. Let's get into write that. So we want to bound star. So let's just write star. Let's open out what star is. Star is exactly. So let's just recall. It's x1, x2, xt. Randomness for all I in t. Xi is in b. Now I'm just going to open out this probability in this one. So this is the summation over all possible. What can x1, x2, xt be? They can be t vertices. Let's go over all possible v1, v2, vt, which are in B. And this is a probability that you start with x1 being v1, x2 v2, xt vt. This is just, I've opened out the probability massively. So I've taken the probability, written it as a summation of mod b to the power t terms. Okay. But now we know we can write this down. It's a random walk. We can write down this expression. What is this expression? v1, v2, vt belongs to b. So it's a random walk. What's the probability that the first step is v1? It's exactly, because you're picking the first step uniformly at random, that's exactly the stationary distribution, pi of v1. That's the first step. Now, given the first step, you have to move from the first step to from v1 to v2. That's exactly the probability mv1, mv2. That's a random walk. So that's what's. Now from v2, you need to move to v3. So it's mv2 times v3, and so on all the way up to mvt minus 1 vt. The people. So far, I just written down, there is a random walk, t steps. So how do you get this? You have to pick the first step at random. So that's pi v1. Now from the first step, I need to go to the second step. That's exactly this probability. From the second vertex, I need to go to the third vertex. That's this probability, and so on. So this is exactly the probability that we care for. Questions? Now, fine. This is the exact expression that I want. Only problem is that I don't have handle on what this set P is. P is an arbitrary set of density mu. I would like to bring, if the summation was over all vertices, then I could possibly do something. So what we will do is, we will modify it so that I can write it as a summation over all vertices. We will bring in the other vertices also, but zero out all those terms. So we are going to come up with a vertex. Let's come up with this matrix. So let's look at indicator of B is the function, is just the indicator that V is in B. I'm going to look at this thing. Let's look at this matrix P. It's a V by V matrix. Let's split it up into two parts. The vertex set is B, V minus B, B, V minus B. And let's put the identity matrix over here, 0, 0, 0. And this is a matrix P which I'm going to go. Notice this is exactly the diag of 1B. It's the matrix. It's a diagonal matrix which has 1B on its diagonal. Okay. So once I have this, I want to claim, now I can, if I have this matrix, now I can rewrite star in the following fashion. Star is just V1, V2, Vt. Now over all vertices, not just vertices in B, phi V1. But then I will put P V1, V1. This will check if the first vertex is in B or not. If it's not in B, this would have gone to 0. Then M V1, V2. Then I'll check whether the second vertex is in B, that's P. Then I multiply it by M V2, V3. Check that the third vertex is in this, and so on all the way. Now I'll go all the way to the team vertex is in B. MV1, MVT minus 1 VT. And I have to finally check also the last vertex is in. It's this product. This is okay. So the difference between this expression and this expression is this expression goes on. This expression goes only over V1, V2 in B. This expression goes over V1, V2 in all of capital V. This is in B, this is in V. And of course, these two expressions are the same because the other terms are, all the other terms which don't appear in the summation are all 0. P will take care of, it's going to zero out all those terms. Is this fine? So far I have not done anything. I just rewritten things. Now why have I rewritten things like this? At this point, now this should look to you like matrix multiplication. It's the matrix, there's a matrix P, there's a matrix M, there's a matrix P, and you're going over all this one. So this is exactly, it's exactly, if you look at this, this is exactly the matrix P, MP to the T minus 1. So it's this matrix multiplication. That's finally a vector, and you are taking the one norm of it. One norm is the usual, when I mean a vector is one norm, I just mean summation mod V. Okay, this is, you're just opening out this. One second. Sorry about that. So just staring at this, the reason, this is exactly this quantity. Just stare at this for a while. It's not hard to realize this is this quantity. Questions so far? I have done nothing so far. We have just rewritten the probability which we want to analyze in a more convenient form. We're going to massage it in a still more convenient form to finally in which we can, now we apply the spectral gap. The factors. Questions so far? Please ask me. Otherwise, I feel I lost all of you. If I can't see faces, I can't. Assuming everybody is following over here to ask me. So it's the one norm over here. So we defined it in terms of this one norm. But this one norm is not the nice one norm. When you're working with the inner product, it's better to work with the usual inner product. So I'm going to rewrite this as, what is this? So this is the same as this fall. If you recall, this is the same as this probability. P, MP, T minus 1, 1, 1, 5. This is exactly this inner product between them, because if you notice this object over here, this pi is exactly taking care. The inner product has that pi multiplication in it. It's the pi inner product. So this is just moving to the pi, rewriting in terms of the pi inner product. Okay. But now we can say certain things on this. We can now apply Cauchy-Schwarz and all. Now we have something. We know some, once you come to the world of inner product by writing in these words, now we can hit it with certain things. But before that, I want to make some more this ones. Let's look at this. Are people with me or have I lost you guys? Please ask me questions.
Just a small,
if you don't cover.
Small doubt. So pi is a column vector, right? This should be pi transpose or
Which one?
in the one norm.
Yeah.
So let's actually
equation.
let's rewrite this. Let's rewrite this step a little more. I could have skipped this first step. What is this? This is exactly summation v in v1 and v pi v1 pmp t minus 1 1 at v1. Is this what it is? No, this is this what? No, 1 second. No, what I written previously was the object. What's the object? Let's see if it's pi pmt t minus 1. It's the one. It's exactly that object. Now notice what is this? This guy. This guy is summation. It's a summation v going from summation v in v pi pmp t minus 1. It's this at the vth vertex, the absolute value of this. You can theoretically. By the way, everything is positive. I don't have the absolute value. This is exactly pmp t minus 1 1 1 pi. If you open this out, you'll notice this quantity is exactly the other quantity. Let me write it a little more differently so that it's more obvious. So this one I want to write, this is exactly summation. Or even the previous statement, I want to say it's exactly v over v pi v pmp to the t minus 1. Apply this on 1, all ones vector, take it at v. And if you notice the expression above and this expression are the same object. Actually ignore this intermediate step, ignore the intermediate step completely. This object p2 all the way up to pt minus 1 is exactly pmp t minus 1 at v, and then I'm multiplying it by pi v. So this is, so actually let's ignore this statement, let's forget about this intermediate statement. I want to say that this quantity which I written above is exactly this quantity, because the second part p all the way to this. What did I do? This part, p all the way to this, is exactly pmp t minus 1 applied at the vector 1, the v1th component of that guy. That's exactly this, and that you're multiplying it by pi v1. So this is, in some sense, this is the inner product between pmp t minus 1, 1, the all ones, because I'm just multiplying everything by 1 with the pi in product. Ishan, is this more clear now?
Yes.
You'll have to get a little comfortable with this, but
Yeah.
this is, you write it down, this is exactly the quantity we care for. So now let's come to this step. Let's assume you have come to this. Just stare at it for 5 minutes when you should be able. Actually, it should be clear for the way I have written it right now. That is, this quantity, this pi v1, I'm rewriting as pi v. This part is exactly matrix multiplication, and you're picking up the v-teeth guy. That means pmp, I'm applying on the vector 1 and picking up the v-teeth guy, v1th guy. The v1 will be the guy left over. So this quantity, this is exactly this quantity. Convince yourself of that. But once you convince yourself of that, this should be, the fact that this is equal to this should be clear. Ishan, do you have questions on that, or is that fact that this is equal to this should be?
Yeah, that is apparent. The first part, yeah, it's okay. I'll have to stare at it.
You'll have to open this out. Convince this is just regular vanilla matrix multiplication. Convince yourself that is matrix multiplication, and that's the whole reason for going from V1 V2 B to V1 V2 V. Therefore, I can write down a matrix multiplication form of this. Convince yourself that this is the case. So all I want to do is all of this manipulation was just to get star to this more convenient form to work with. Okay. Now, once we have that, I want to say we can do two more. I want to apply Cauchy-Schwarz on this. But before I apply Cauchy-Schwarz on this, notice that this quantity, this guy, is it supported on all this vector? Is it supported on all the n vertices, or is it supported only on vertices which have support in B?
B, only on B.
Only in B. Therefore, because of that, whether I put this or 1B over here, this will not change. Because the left-hand side of the inner product, the left argument of the inner product is only on B. Therefore, the right argument also I can put it on 1B. I can zero out the other guys. I can just zero it out. Now, since support of P, MP, T minus 1, 1 is in B. But now I want to say, this one also I can change it to 1B because I'm hitting it with a P anyway. That P is zeroing out. I'm hitting it with a P here. That the rightmost P is anyhow zeroing out. Remember, P is this matrix. The rightmost P is anyhow going to zero out everything not in B. So I might assume this guy is also P MP to the T minus 1, 1B, 1B. Since this is because P of 1 is the same as P of 1B. Okay. Now I'm going to just apply Cauchy-Schwarz to this, say that this is at most P MP T minus 1, 1B, 2 pi now times 1B, 2 pi now. This is just applying Cauchy-Schwarz. So let's keep let's calculate the easier thing first. What is the 2 pi norm of 1B?
Mu.
Huh?
Square root mu.
Square root mu. The square of the norm is mu, and then you have to take a square root. Therefore, this is square root mu. Square root mu. I've done this. I'm going to do one more step to this. I'm going to write this as. This PMP. This is nice. I'm going to write this as PMP to the T minus 1, 1B, 2 pi times square root mu. This is just because since P square is P. Notice this thing has I'm put all the in-between P's there. So it's PM, 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 PM. Now I'm making it PMP, PMP, PMP. So all they were in between. The in-between P's were just 1 previously. Now I'm making it a square. And that's just because P square equals P for the matrix P that we care about. It's just because this is a nice matrix product. This is just the matrix power. The reason for doing this is a matrix power. Instead of carrying out these two, I'm working with this guy. Okay. So what we want to understand is what is the norm? The question we are now left with, what is the norm of PMP T minus 1, 1B. So I take the vector 1B, I hit it with PMP T minus 1 times, and I want to know what's its what's its two norm after doing this? This is a question which we want to ask. So in general, to ask this, so how large can this value be? So we'll do something more general. For a general operator, M on RV, a linear operator RV to RV, we'll define the norm of the operator to be the maximum it stretches any vector relatively. Notice this, if you're familiar, this is the largest eigenvalue. If eigenvalues exist, this is the largest eigenvalue of M, if one exists. Let's define this object, because this is why I want to find out the norm of, PMP to the 1B. I don't know how to do it for the specific B, therefore I'm going to define a more general thing, find out if I can do for that setup. Let's make some quick observations of this norm. What is M1 plus M2? How does it relate to M1 and M2? Does it have some triangular inequality of this type?
Yes.
It follows from the definition of max. The max, this one is max of a quantity. This just follows from the definition of max. This also will follow from the definition of max. Suppose you had product M1 dot M2. This is also less than M1 product M2. And both these follow from the, because what is this? What is the first? The second one is more obvious. What is the norm of a matrix stating? It's the maximum amount you can stretch a vector. So it is stating the maximum amount the product can stretch is the maximum amount the first guy can stretch, followed by the second guy. That's the maximum. Possibly it can't be that large. It possibly is much smaller than it, but that's the maximum it can be. Similarly, the maximum that the sum can stretch is the maximum each individual guy can stretch plus the sum. So this is all that we have. So let's just keep this aspect of this one and let's go back to star. So what did we need to calculate? We needed to calculate, going back to proof, we needed to calculate the norm of PMP to the T minus 1, 1B. Notice by definition, this is just the norm of this guy, 2 pi times the norm of 1B. That's just the definition of, it just follows from the definition of the norm. This is just coming from definition of the norm of a matrix. This is PMP to the T minus 1, 2 pi. 1BP is, we already saw it was root mu. And this, by what we have seen, is this is just PMP 2 pi T minus 1 into root mu. Okay. So returning star, plugging this back into star. Star had both this expression and a root mu. This expression itself was something and a root mu. So plugging back into star, we get that star is less than or equal to PMP 2 pi to the T minus 1 times mu. Okay. So now the question is, what is PMP? It's sufficient if we understand this. In fact, it suffices to show PMP 2 pi is less than or equal to mu plus lambda 1 minus mu.
The first inequality, I think I missed again. So
Which
this
inequality?
definition of the norm of the matrix.
This one. So you're asking this guy.
Yes.
This is definition of what is a norm. Norm of a matrix is the maximum stretch you can get. Therefore, I'm asking what is the stretch you get with 1b? It is the norm of the matrix times the norm is the maximum stretch. It's a stretch over all vectors, and in particular instantiating with the vector x being equal to 1b.
Yeah, got it.
Yeah, it's just the definition of the norm. Norm is a maximization over all this. And I don't know if 1b is the vector that has the largest stretch, but certainly it's better than, it's at most the norm of the matrix. Okay. It's a long thing, but if you actually look, it'll take a while. Right now, it seems a lot of calculations going on, but if you look at it carefully later on, it's going to be it's a natural thing to do once you have the vector, sort of this eigenbase decomposition of this one. But let's continue with the proof. So what we're asking is this next question. We need to ask this, and notice that it suffices for the proof. To complete the proof, all we need to show is this. If we show this, we will be done. Okay. So now let's try to show this. But actually, even before showing this, let's do a warm-up case. Let's do a sort of the baby case warm-up when M is actually the independent, M is the independent random coin toss case. That is, G is the complete graph with self loops. In that case, do I know how to bound this PMP to the 2 pi? So let's stare at let's call it M independent at that point. What does M independent look like? So M independent, notice that it doesn't care where you are. No matter where you are, the next step is picked according to the uniform distribution, pi from the top. That's what the stationary distribution says. Basically, that says that every row of this one is distributed according to pi. It just says, I don't care, no matter what the distribution is. So no matter which P, this is the thing stating that no matter which P you put, when you put M end of P, you will get back pi. That's in one step you go to the stationary distribution. That's the M independent thing. No matter where you are, in one step you go, and this is what happens. This is because since P is a probability distribution. This is because each row pi is exactly if you come up with the vertex B, what's the distribution you see? That's the distribution B. A row in this matrix is exactly what does the random walk tell you? If you see, the ith row is what is the distribution induced by the random walk on the vertex, and the independent random walk, the distribution induced is actually the stationary distribution pi. For every vertex, it's pi. Therefore, the matrix correspond to M end looks at this pi on every row. So let's look at for this particular matrix. So this can be more succinctly written as J times pi, where J is the all ones matrix and pi is, as before, it's the diag of the diagonal matrix which has pi along the diagonal. Okay. Now let's look at what is P M ind P look like. This is, notice it's B. That's what P looks like. M end looks like pi. Just a second. Sorry, there is a meeting tomorrow and I have things to attend to it. Yeah. Anyway, so this is P, M and P. This is what we do. Now let's open this out. What does this guy look like? This post multiplying by B is going to knock out all this. Is not going to knock out all this part of the matrix. It's going to make this 0. Pre multiplying by P is going to knock out this part of the matrix. So in fact, if you look at it, this will look like, if you look at this matrix, this is once again, this will be B. It will just put pi restricted to B and then 0. There's a big 0 over here. There's a big 0 over here, 0 over here, 0 over here. It's going to be pi restricted to B. This is the matrix that you will get. P, M, and P will look like this object. Okay. Notice this is a rank 1 matrix. Because every row is a sort of scaling of the first row. Every row is a scaling of the first row. Either it's the same first row or it is 0 times that row. Every row it's a rank 1 matrix. Therefore, it can have only one non-zero eigenvalue. And if you stare at this a little more closely, you will notice that P, M, ind P, when applying on 1B, is actually going to give you pi of B times 1B again. So basically, apply 1B on this, and you'll notice that this exactly gives you pi B times 1B. Therefore, 1B is the eigenvalue. 1B is the eigenvalue, eigenvector, possibly not normalized, for Pm ind P with eigenvalue pi of B, which was mu. Therefore, this in particular tells you Pm ind P, the 2 norm of this, is exactly mu. Because that's a rank 1 matrix. It has only one non-zero eigenvalue. So the largest eigenvalue is this quantity, and you already have exhibited explicitly what the largest eigenvalue is. Okay, all of this is for M and. Notice now this recovers the independent case, the case which we knew how to prove mu power t, which I think Varun or somebody pointed out at the very beginning. This recovers if the graph was mu power t. All of this machinery said you can prove mu power t. It's a very complicated way of proving mu power t, which we knew how to do. But I want to say with a slight modification of what we have, we can actually get the final result that we care for. So is this part clear that this proof requires you to go think about it a lot? Is this clear why this PMP in PM and P of 2 pi is actually mu? Because it's a rank 1, but we actually explicitly written down what the matrix is. And I want to find out what is the largest stretch. And it's a rank 1 matrix. Therefore, the largest stretch is the largest eigenvalue. And because it's rank 1, it is the only non-zero eigenvalue that you can have. And that we have explicitly said this is the eigenvector. The only non-zero eigenvalue out here is mu. And therefore, that is what do you mean? That is the norm of this vector, of this matrix. But what we want is PMP 2 pi, not PM ind P 2 pi. So what we'll do, the idea over here is going to be write M as a combination of M ind and an error matrix. What do I mean by that? Let's stare at it a little more. So what is M? M is an operator. It's completely described by what it does to the basis vectors. So the basis vectors, which is V1, which is the all ones vector, it maps it to the all ones vector V1. V2, it maps it to lambda 2 V2. V3, it maps it to lambda 3 V3. and so on, Vn, it maps it to lambda n Vn. That's what. What about M ind? What does it do? It maps V1, the all ones vector to V1, and because it's rank 1, now everything else it has to map to 0. Vn to 0. So now let's come up with this matrix ME. I'm going to specially design it for the following way. It takes V1 to lambda V1, V2 to lambda 2 V2, V3 to lambda 3 V3, and Vn to lambda n Vn. Notice the way I have set it up, it has the property that M is actually 1 minus lambda times M ind. It's exactly scaling of this plus this error matrix. This is as an operator, this is what it does. And this will be a useful fact. This is called the matrix decomposition of the random walk matrix. And this will be very useful for us. We'll be done with the proof in 1 minute. This matrix decomposition of the random walk matrix, and it will be useful actually even in the next lecture. In the explicit construction, we'll use this matrix decomposition. So we have this. What have we said over here? We have said that any matrix in the random walk matrix, can be written as a linear combination. It most of the time looks like the independent matrix plus some error. And how large is this error? Let's stare at this error. How large is this error? So let's look at the norm of, let's understand what is this object, ME 2 pi. Let's try to understand this. So basically I want to understand what's the stretch when I move from X to MEX. So let's just write X in the eigenbasis. So let's write X as alpha I Vi. Therefore, X 2 pi is just alpha I square. What is MEX? By definition, this is alpha 1 lambda V1 plus I going from 2 to n alpha I lambda I Vi. Therefore, the norm of MEX, the true norm of this, is exactly alpha 1 square lambda square plus I going from 2 to n alpha I square lambda I square. Now lambda is the largest among all of these guys, absolute value. Therefore, this is lambda square times summation alpha I square, which is lambda square mod X 2 pi. Hence, by the way, everything is in us. This is a square. Hence, mod ME X 2 pi, the stretch is lambda, rather less than lambda. That's the conclusion of this. So what am I stating? That if, or the conclusion of this object is this following fact. If M is a random walk matrix with spectral gap 1 minus lambda, then M can be written as 1 minus lambda times the M ind plus an M error, where the M error has very small norm. Its norm is at most lambda. Okay. We are now finding shape. We needed to calculate this object, PMP 2 pi. We write this as P of 1 minus lambda M ind plus ME P 2 pi. Now you use additivity to say that this is at most 1 minus lambda PM ind P 2 pi plus PME P 2 pi. This we already saw was mu. This is exactly what we calculated. And we need to calculate this object, PME, P 2 pi. This is less than 1 minus lambda mu plus, once again, multiplicativity of the norms. Now, each P can only make things smaller. It's a projective object. Therefore, the norm of each P is at most 1. Therefore, this is at most 1 minus lambda times mu plus ME. Since P is as norm less than 1. And this, we already saw, it's 1 minus lambda mu plus lambda. That's the end. It's a long proof, but this is exactly what we wanted to show. Recall, it sufficed for us. There was a previous statement somewhere. Where did I say? It sufficed for us to prove this. PMP was mu plus lambda 1 minus mu, and that's exactly what we have proven. Oh, sorry, I should have written it. How did I write it? So I'm going to. So this is the same thing as lambda plus. Sorry, how should I write this? This is 1 minus lambda mu plus lambda. These two are the same quantity. So we have thus proven. So we had this whole exercise. We had the star. So star probability was norm of PMP to the t minus 1 times mu, and this is exactly lambda plus 1 minus lambda mu whole to the power t minus 1 mu. This quantity here is the same as mu plus. Am I making some mistake over here? Mu plus lambda 1 minus 2. This is how the expression. Okay. Question. It's a long proof. But we've done every single step of the proof. You just go and look at it carefully. It's a long proof, but it's actually very nice proof. It explores the spectral decomposition. It's a very nice success theory of the spectral decomposition of expander graphs.
So just to add a minor point here,
Yeah.
I don't know, I remember when I first saw this was very insightful. So the point is, we did use multiplicativity of the norms in the PMEP calculation, right? When we wanted to do that. Now the question is, one might ask, why can't we do the same thing with PMP? The problem is that P has spectral norm 1. That is, there are some vectors that P actually does not change at all.
Yes.
Similarly, M also has spectral norm 1 because M has this stupid, the stationary distribution or whatever, the all ones vector, which doesn't change at all. So if we use the multiplicativity, it feels like, oh, the spectral norm of PMP is just 1. That would give us nothing. The key point is that the vector that P does not shrink and the vector that M does not shrink are sort of far apart. Like the vectors that P doesn't shrink are completely supported only on the B part. Whereas the vector that M does not shrink is actually spread out everywhere. And what this is really exploiting is the fact that these two vectors are very different from each other. So you want to say, if you apply P followed by an M followed by a P, every vector is shrunk by some decent amount because the vector is bad for one of these things. I mean, it can't be good for all of them. So that's really what is being exploited here. Yeah.
Okay. Any other questions, comments? I'm going to take an extra. I have 5 more minutes, but I'll possibly take another 5 minutes. I just want to do one thing to set it up for the next lecture. But before that, I want to ask: is there any comments so far? It's a long proof. Stare at this proof for a while. Go over, have a look at it. It's a slightly different treatment from what Salil does in his notes in his pseudorandomness manuscript, but it's the same sort of proof. It's this one. So he sort of defines the matrix decomposition early on and says this is an equivalent characterization of spectral gap. The way I sort of did the proof was I pushed it all the way to the end till the point where we actually need it. And there it was clear why we wanted to do it, why the matrix decomposition came, why we split the matrix M as something which depends on the independent matrix plus this decomposition. It's a useful decomposition. And we'll see yet another application of this decomposition in the next lecture when we explicitly construct expander graphs.
Can you once show the proof of this matrix decomposition just above this where we proved?
So no, the matrix decomposition was just this. So M we knew was this object by definition.
Mm-hmm.
Is this operator. M independent is this operator. It takes V1 to V1, the all ones to all ones. Once it does that, everything, that's the rank one thing. Therefore, everything else, it has to take it to 0.
Yeah.
So M independent is this. So ME is just set it up so that this equation is satisfied.
Okay. Okay. Yeah. Okay.
And then I analyze what is the norm of ME by this property. So I'm stating, so ME is just set it up so that M is like M. Most of the time, 1 minus lambda of the time, M looks like M end plus some error term. And then I ask what is the norm of that error term, and that I calculated it out here and showed. Therefore, I say that if M is any random walk matrix with spectral gap 1 minus lambda, then M can be decomposed as 1 minus lambda. It looks exactly like the independent matrix, 1 minus lambda fraction of the time, plus there's an error term, and the norm of that error term is at most lambda. Okay.
Yeah. Okay. Thanks. Yeah.
Okay. So far, we've seen all these nice applications of expander graphs, but eventually, we need explicit constructions. We need to have explicit constructions of expander graphs. And recall, we had two notions of explicit, which we call explicit, that is, if it runs in poly in the size of the graph, poly in n. This is sometimes also called mildly explicit. And then super explicit. If it is given V in n and I in d, can calculate the ith neighbor of V in time polynomial in its input length, that is poly in log n and log t. Then we call it super explicit. This is sometimes called, instead of super explicit, it's called fully explicit. Okay. I'm going to give examples of two sets of graphs which have these properties, and the next lecture will actually give a completely different construction. So what we'll do today is we'll see three algebraic constructions of explicit expander graphs. I'll do that without proof. The first one is the following graph. Let M be any positive integer. The vertex that we look at is Z integers modulo M cross integers modulo M. So it looks like the vertices looks like basically x comma y. X is in 0, 1, 2, M minus 1, and so is y. So it just looks like this pair. Right? And I'm going to connect the vertex xy. Its neighbors are, there's going to be a self loop. It's connected to xy itself. It's going to be connected to x plus 1 y. Now, because I have to make the graph undirected, if it's connected to x plus 1 y, it should also be connected to x minus 1 y. It's connected to x y plus 1, which will make it, to make it undirected, it also connected to x y minus 1. X plus y. So it will be connected to x y minus x minus y comma x. This will be y comma minus x. So this is a 9 regular, notice it's a 9 regular graph. And the surprising thing about this is one of the earliest explicit expander graphs. Margulis showed that this particular graph actually happens to have a spectral gap. It's a super explicit graph. Notice it. Laptop is asking me to stop. I will continue for a few more minutes. So it's a theorem of Margulis.
But plug in your charger and then do it. I mean, this will die in 2 minutes.
I do not know. I charged it to 100% yesterday. Let's see. The theorem of Margulis. No. What happened? Margulis is there exists a lambda less than 1 such that for all m, the above graph is a 1 minus lambda spectral expander. So it's a fixed gap no matter which n is. So they're larger and larger graphs which all have this fixed spectral gap. It's one fixed spectral gap for some number. So the first example we'll see. The next example is also a very nice example. The vertex set here is the primes, the 0, 1, 2, 3. So P is some prime. Plus I'll add to it.
FP contains 0 anyway.
Sorry, I wanted to add the point at infinity.
No.
Felberg, you can do 2 ways of doing it. It depends
Oh, okay.
on. So you don't put 0, you put 0.
So yeah, I sort of collapse 0 and infinity.
Okay, so then let me write it this way. It's going to be it will be a 3 regular graph. In which the number x is connected to x plus 1. Because of that, it should also be connected to x minus 1 to make it regular, and 1 by x. And the convention is, we will sort of say 1 by 0 is 0 over here. So there's a self loop. So it's sort of, think of these things as 0, 1, 2, 3, all the way up to p minus 1. So every vertex is connected to one below it, one above it. It's also connected to its inverse, sort of these guys. So there are these sort of lines, and there's a self loop over here. This is how graph looks like, and the famous theorem, 3/16 Felberg Theorem, it says that there exists a lambda, once again lambda 1, so that for all p, this graph is a 1 minus lambda spectral expander. Okay. Notice the first graph, the Margulis construction which we gave here, was a super explicit construction. I gave you a vertex. You could tell, if you tell me the fourth neighbor here, I give you the vertex label, and I tell you, give me the fourth neighbor. You can compute this extremely efficient. What about this object? Is this also a super explicit graph?
Inverses can be calculated efficiently due to Euclid, I think.
Is somebody saying something? I
couldn't hear properly.
Huh? Was somebody saying something?
So I think inverses can be calculated efficiently due to Euclid's algorithm.
Yeah.
So x plus 1 and x minus 1 are already something that we can compute. So this should be also super explicit.
Yeah, it seems as if it's super explicit. Only thing is, how do you get the lay your hands on a prime p?
Oh, I see.
The only way I know it is pick it randomly, and that defeats the whole purpose of this. So once I know what the size of the graph is, then everything is super explicit. But I don't know how to get the size of the graph. I'd lay my hands on a prime p, and the only way I know to do it is pick it randomly. So it is not super explicit. It's explicit because you have to. I don't know how to pick a prime p deterministically. Yeah. So if you believe the generalized Riemann hypothesis, of course, this is a super explicit construction, but we don't know how to pick a prime P. The last construction which I will see, I will stop with this. I'm already short with 6 minutes, but I will finish this and I will wrap up. This is because the point of doing this is we will not be doing these. These are constructions which we are going to take without proof. These are depend on Fourier analysis or sort of profound theorems in number theory. What we will do next lecture is not prove any of these graphs. We'll take a completely different construction and show that it's an expander graph. These were the original constructions that came from math. We will give a construction that was proved in the computer science community in 2004 called the Zigzag expander construction. I think Ram Prasad will do this in the next lecture. And this notion of explicit, super explicit, we will see it even more clearly when we do next lecture. The difference between the two will be made extremely clear. But let me do the final construction and then stop. The next construction is due to Lubotsky. This is a very celebrated expander graph, Sarnak. And it goes this way. Let P be some prime, so that P is 1 mod 4. Q is some prime power. The only restriction of Q is Q should not be equal to P. It could be P power K, but it's some prime power. It need not be. It could be some other prime power too. But Q should be a square mod P. And there must exist a I in FQ such that I square plus 1 is 0. And this will happen. You can notice this. Let's look at this set. This thing construction will seem strange, but let's look at the set which are A0, A1, A. I haven't yet described the vertex set at all. A1, A2, A3. I'm just defining some other object now. These are objects in Z to the 4, which have the property of the following. A0 is an odd positive integer. A2, A3, A4, sorry, A1, A2, A3 are even integers, and their sum of squares is P. What is known as the number of A's is that this number is actually P plus 1. This is sort of known, the number of such objects. Now, what we will do is we will define a graph on FQ union infinity. That is the number of vertices, that is the vertex set N is Q plus 1, which is mod A regular. And what's the neighborhood, the particular, so the A0, A1, A2, a third neighbor of a Z in FQ union infinity will be this object, A0 plus IA1 plus Z times A2 plus IA3 minus A2 plus IA3 Z A0 minus A1. And the celebrated theorem of LPS, Lubotsky-Phillips-Sarnak, says that this graph for all prime powers Q, this is actually Lubotsky and then Morgenstern, for all prime powers Q, this graph GQ has spectral gap 1 minus lambda, where lambda is 2 square root P by P plus 1. Okay, now you'll ask me why I did this first. If you look at this number is 2 square root D minus 1 by D. Notice that this is D, this is the degree. So they managed to construct this graph, which beats the random construction. So these graphs are what are called, in fact, these were the first known Ramanujan graphs. They come very close to the Alon-Bopanna bound. Random graphs are a little more, they have an order 1n, this achieve it. These are the best, these are the graphs which have the best spectral gap, this one. And this is a construction due to LPS. Written these three constructions. This is also a super explicit construction, by the way. The LPS, you just stare at it, super explicit. We'll ask why here a prime, but the point is the graph is on q power k, the prime is p, therefore it can be made super explicit. You can make p, the prime power to be much, much larger than this and make it super explicit. There are three constructions. These are not the constructions which we will be constructing next lecture. Next lecture, we'll actually give it a different construction called the zigzag expanders, which is an super explicit construction. It will also have the properties like Margulis. It won't be the only difference from these constructions. It won't be Ramanujan. But on the other hand, it will be a super explicit construction, and we'll see this next time. Sorry for going over time. I'll stop with this. Any questions? Yeah, the advantage with the construction next time is we'll actually see the proofs that it's expander. Right now, this was all, I just quoted proofs. I quoted Lubotsky, Phillips, Sarnax, Margulis, Felberg. These are profound theorems in number theory and Fourier analysis needed to prove these things. We won't do this. We'll actually prove it from scratch, just using, in fact, the matrix decomposition, which we mentioned last time, will come very useful in proving it next time. Questions? Yeah, today was a heavy lecture, just like Ram Prasad pointed out in the chat. Look at the proof is long and windy, but just find out what happens when you have the independent set. Why does the proof work then? Give us the whole proof is actually trying to give a spectral proof why when you pick it independently does work, and modify that proof to the expander case. That's how you have to look at the proof. So we gave a convoluted proof for mu power t, and then showed that that same proof can be modified to get it for expander graphs also. Okay, I'll stop with this. Any questions?